So this is another interesting part. Again, we talked about the geometrical logic behind, or the geometry, the spatial logic behind. Now we need to talk about the time part of the logic. And as I mentioned, FLAC2D and FLAC3D actually solves dynamic equations of motion, even for static problems. And that's done intentionally because it's a very generic approach. It allows us to really follow very nonlinear paths in time and space. It allows us to take small increments in time. That's actually how we bring time in the picture. But for those of you who dealt with dynamic analysis, you know that typically dynamic problems require a very small time step. If you solve static or quasi-static, or if you're dealing with static or quasi-static analysis, having this tiny time step to come up to arrive at the solution will be very impractical. So we actually playing games with time step while solving dynamic equations of motion. And that time step is shown here. If we consider, just to give you an idea where this comes from, if you consider simple example, let's say a ball on a spring bouncing. So this is called harmonic system. So based on third Newton's law, the deformation of the spring is equivalent to the F equal ma of the ball, so mass by acceleration. So we have, this is essentially the basic harmonic equation in 1D. We have on one side ma, on the other side minus kx, the deformation of the spring. So ma, it's second derivative of displacement in time. If you put this here, zero. This is our harmonic equation of motion, or basic dynamic equation of motion. Basically, if I fuse further, the same. So this is actually a damping parameter. We can typically it's written like this: x over some damping parameter a, and so we get this actually a squared. That's where we get this expression essentially. In reality, it's a bit more complicated because we actually write this equation in 2D or 3D. But here's one important thing. This mass typically consists, like it's a mass of a grid point in our numerical model. In this equation, we call it inertial mass, and it's different from gravitational mass. This inertial mass only affects the dynamic system. So it doesn't truly have a meaning of true mass. Or for us, it doesn't have a meaning of true mass in this equation. So we can actually change it in a way. This is not dampened, this is time. This is called time step. So this is characteristic time step for the model. We can change this mass in a way that our time step will be 1 without affecting true mass of the system. And this is done just to have larger time step. So we separate gravitational mass from inertial mass, and we modify the mass of grid point to some fictitious mass in such a way that this dynamic equation of motion is solved with time step equal 1. Again, this time step has no relation to reality because we modified mass. And we're actually solving static system. In reality, there's no time step. If you deal with dynamic analysis, this time step becomes real time step, also with creep. And the masses become real masses. So there you deal with real small time steps. But for static or quasi-static analysis, this time step can be modified. We modify it in a way that this inertial mass is pretty much the same as stiffness material. Stiffness is calculated from bulk and shear modulus. So that's why this time step is not real time step. But we use this time step to equilibrate our dynamic system and arrive at static solution. Obviously, if the stiffness is higher, this grid point will have higher inertial mass. For you, you don't really care about this inertial masses. There's no need to track them. They're meaningless physically. What's important is in how many steps or how fast we arrive in final solution or static solution. And for that, we use local damping. Because let's say if we have this ball on a spring and we bounce it, if there's no damping, it will bounce forever. We need to introduce damping, which is equivalent to friction. And in dynamic systems, damping is typically proportional to velocity. This is called velocity damping. We use different approach. We use so-called local damping, which is proportional to so-called out of balance force and to the sign of that force. And that equation is provided here. So essentially, what it means that we track how the system is going away from neutral position and how far it goes away, what kind of forces on the grid point level, what kind of forces applied to grid point. And then we, let's say if it goes down, we push it back up, essentially apply a force with opposite sign and multiply it by damping coefficient here. So this way, our damping is not proportional to velocity. It's proportional to force, out of balance force, multiplied by opposite sign and multiplied by damping coefficient. If you remember, well, if you remember from your university classes, the classical harmonic equation with damping, something like this. Let's say there's damping coefficient alpha multiplied by velocity, and if you go in these terms, something like this. So we have second derivative in time, first derivative in time, and just displacement. So we do damping differently here. We do it this way. And this is really beneficial because we dump system really quickly when it starts oscillating around the static solution. And we get to the results really fast this way. However, there are other cases when you have actually plastic deformations and material flows. And the velocity doesn't change. Let's say it's constantly deforming in one direction. So this type of damping not going to help there because there's no neutral point. It's already plastic failure, let's say. And the deformation goes in one direction. This is, for us, it's still acceptable solution. We can stop solving, like we don't need to iterate and forever to see how material deforms. You basically see material deforms and continuously deforms. But we still need to stop this iteration in time somehow. So in that case, we actually use this velocity proportional damping in classical dynamic system. And sometimes we can manually specify that I want to dump my system faster by using this approach. And this is, for us, we call it combined damping. We essentially use both force proportional damping and velocity proportional damping. Let me show you a very quick example. This is Prandtl's problem from documentation. You can just let me open FLAC2D. I actually will show you how to get some examples from FLAC2D. Prandtl switch problem. This one. I'm going to open this project. I think. So first of all, if you go to help, examples, you can see FLAC, and there are a bunch of different examples here that you can open and study. They're also listed in documentation. You can go to that online help and basically find most of these examples there. So that's, if you just want to learn something, you can go here, for example, user's guide or verification problems. And the example that I'm showing here, it's in verification problem, it's this Prandtl switch. Prandtl switch is essentially a plastic Moore-Coulomb material on which you compress with just flat wedge, and it's trying to calculate bearing capacity of the soil. Basically, bearing capacity is how much force the soil can withstand before it plastically flows from the outside. And basically, you'll see this pattern, this flow pattern from outside the punch. And that has an analytical solution. So this is one of the cases where we can easily test how well FLAC2D calculates results. Let me just run this analysis. So this is a data file. First, we create geometry. We specify material properties. This is again a little bit about geometry. This is boundary and initial conditions. This is a little bit of scripting to define where we calculate forces at which positions near the punch to calculate bearing capacity. Then we track histories of different parameters and at different locations. And basically, we just solve it. So let's see if I execute this file. Let's see what we're going to see. See that the punch is essentially pressed here, and it starts flowing. The material starts flowing this way. See how it flows here. So this is kinematically acceptable solution for us, but it's not truly static. If we continue pressing, the material will continue flowing. It just never stops. But we need to stop analysis somewhere. So that's where that damping really plays a role. It determines for you where to stop the analysis. And we can see that our results, this force was calculated, I think, on the edge of the punch there. It approaches the analytical solution with time after a certain amount of iteration cycles. So at the end, we get exactly analytical solution. So here we used the force damping, and you can notice that number of steps required to get to that force damping was around 13,000 steps. Now, if I use different type of damping, which is combined damping, I'm just going to enable this command because it's much more efficient. And I actually need to specify very small damping coefficient because otherwise it will stop really quickly. It will tell me I already had the solution. And it's going to be really hard to see what's happening. So if I run this analysis, it stops faster. And that's it. It required about 9,000 steps. So 4,000, 30% less iterations using different type of damping. So for the calculations where you expect large plastic deformations, kind of unbounded plastic deformations, where they don't expect to stop essentially, material continues to deform plastically. You can use different type of damping, which is combined damping. But in reality, it's rarely used because there's not so many problems like that. If you get failure, you already know that your engineering or your model failed. There's no need to continue calculating it. So another thing, convergence. Again, when we dump the system, it comes to almost equilibrium, but it can oscillate around equilibrium with tiny flashes, like grid point can vibrate a little bit. It's a dynamic system. It still can imagine like each grid point is connected to another by simply like a string. You pretty much dumped it, but there's tiny vibrations. Then how do you know when to stop the calculations? What's level of vibrations or forces acting on these grid points is accessible? So for that, we essentially use a term called convergence. We calculate the sum of forces at each grid point, and we call it unbalanced force. And basically, if the sum of all forces is 0, the system is in perfect static equilibrium. We can stop there. In reality, it's never 0. So we need to specify what level of this unbalanced force, the sum of unbalanced force, is acceptable for us. And typical way how to calculate when to stop is we calculate average unbalanced force for the whole model. And then we compare local unbalanced force to the unbalanced force for all grid points. And that's where we calculate this average force ratio. And basically, when that average force ratio reaches level 1 E minus 5, we say that's good enough. Vibrations are really small. The system is almost at static equilibrium. We can stop calculations there. That's our traditional way how to calculate, how to specify when to stop analysis. However, there is a problem with this because we compare local forces with average forces for the model. But what if we have the system where in one part of it we have large unbalanced forces and another is very equilibrated? We're gonna get on average some force value that may lead us to the solution, but one part of the model will still be kind of changing. So a bit more stringent criterion is called, we call it convergence. We actually calculate this local force ratio just locally. We don't average it for the whole model. And then we compare it, some target value, 1 E minus 4, let's say. And we say that when every grid point in the model reaches that target value, essentially this force ratio, unbalanced force ratio is below that value, that's when we stop. It's a bit stringent, but it allows us to come to equilibrium perfectly everywhere. And it also allows us to say that, okay, I see that this part of the model, which I'm actually not interested in, keeps my model from converging. It's like, it's not equilibrating there. I don't really care that results may be slightly more inaccurate in that part of the model. So I can specify larger convergence criterion there and just arrive at solution faster. While everywhere else, it's also accurate and it's fast. So basically, this way, we can specify different ways how the model converges at different locations of the model. We don't average things. By default, if you just say model solve, it uses the standard averaging approach. This is a bit more stringent, and it's recommended pretty much for all your calculations. This kind of new way how we do it. So this is the final slide about this theory. Yeah, it is the final slide. So how long does the model need to run? First, use convergence criterion. Typically, convergence 1 means that 1 stands for 1 E minus 4. It's just kind of shortcut. Or internally, it will calculate this, use internal value for force ratio 1 E minus 4. When the model convergence indicates that the model is in mechanical equilibrium state, model is in exact equilibrium when force vector at zone centroid is 0. It's never truly possible, but we specify what is acceptable for us by specifying convergence 1 or ratio, different ratio. We can also track maximum unbalanced force throughout the model, and that shows us how the fast model converges. And that's what we're going to track in a few examples of fast model converges. If maximum unbalanced force in the model doesn't go close to zero, it may oscillate around zero. That means that model didn't converge, and there's probably plastic deformations happening somewhere, or plastic flow. So that's where we need to interpret results. We can monitor results. We can monitor histories of displacements, velocity. We can model failure states for each zone, for different zones. For example, if zone plastically fails, it can fail in shear, and it can fail in tension, or even volume. And if, let's say, we model within the zone displacement at particular points, for example, at the crest of the slope, if it converges, we will see that displacement basically doesn't change anymore. If it doesn't converge, displacement continues changing. Same for unbalanced force. If it converges, it goes to zero after some peak, let's say. If it's unstable, it doesn't go to zero. So we can monitor these things. Typically, when model is in static equilibrium, you see velocity vectors randomly distributed throughout the model, and they point to all possible directions, and they're very small in magnitude. That's because each node, each grid point still has, let's say, certain vibrations. We already stopped analysis, but some velocities were recorded. But if there's plastic failure, you can see predetermined velocity field or kind of oriented along that plastic failure, and it's obviously going to be a larger value. By the way, these velocities, again, don't have physical meaning, because remember, we modify the time step. It's not real time step. So it's displacement per the fictitious time step, or per step, per one calculation cycle. So velocities don't have real physical meaning. They only show, they can be thought about kind of relative to something. Let's say this is our zero velocity field, and this is not zero velocity field, showing that things are flowing there, and maybe how fast they flow in comparison to something else. However, we deal with real strains and stresses, and from strains you can derive displacements. So displacements are not part of calculations, but you can plot them, you can put them in a table, list them. Same thing with if you deal like with tunnel excavation. Finally, if you can have multiple stages, let's say multiple stages of excavation. In each stage, you may have plastic deformations, but if it's stable model, you will arrive after each stage at some stable solution. And basically, you may have multiple stages where you can have multiple fields of displacements or velocities kind of stabilizing, or you can see that you can follow this unbalanced force and see how it goes down to zero. And sometimes in intermediate stages, you don't even need to wait until it fully goes to zero. In realistic engineering models, it's quite often acceptable to stop it a bit prematurely, because you will do another excavation and you will equilibrate the final stage. So it's important to equilibrate the final stage.